My name is Georgia, and we are back on the third and final episode on the series of Blatter radicals. Last time we talked about the three main ways of synthesizing the Blatter radicals depending on the different precursors used, which in turn depend on the substituents we wanted on the Blatter radicals. This time we will dive into a completely different aspect of Blatter radicals, their physical properties, and more specifically their magnetic and electromagnetic behavior. Before we're able to do this, however, another question remains to be answered. What is magnetism and how does it come about? Magnetism arises due to the movement of electrical charge. This could be from the current in an electrical circuit to the quantum mechanical properties of the electrons and atoms. Magnetic moments are associated with electrons and atoms. Each electron and atom has magnetic moments that originate from two sources: the orbital motion of electrons around the nucleus and the spin of each electron. Knowing that paramagnetic, ferromagnetic, and antiferromagnetic properties are the most commonly found magnetic properties in radicals, let's look at what these terms actually mean. Paramagnetic materials attract magnetic flux as the flux density in the material increases relative to vacuum. This paramagnetism arises due to the presence of unpaired electrons, as the orbitals are not completely filled, and an overall small magnetic moment exists. In the presence of an external field, these moments align with the field and thus enhance it. There's only a very weak interaction between adjacent dipoles. Just as a reference, diamagnetic materials, in contrast to paramagnetic materials, repel the magnetic flux and arise due to the presence of paired electrons. Ferromagnetic and antiferromagnetic properties, on the other hand, are cooperative magnetic phenomena and give rise to magnetic order. At high temperatures, ferromagnets behave as paramagnets, whereas below the magnetic ordering temperature, i.e. the Curie temperature, a ferromagnet has spontaneous magnetization even in the absence of an external magnetic field. This is because all the magnetic moments lie along a single unique direction. Similarly, below the magnetic ordering temperature, the Néel temperature, an antiferromagnet has its dipole moments cooperatively aligned in an anti-parallel fashion. Interestingly, this anti-parallel magnetic ordering can lead to a magnetic unit cell being much larger than a crystallographic unit cell. Let's now go back to our Blatter radicals. I will use two examples to illustrate these different magnetic properties. The first one is that of a Blatter radical containing a 5-membered 2,1,3 thiazole ring. The spin density of this system extends to the entire thiazole system and is not localized on the benzoyl triazonyl ring. These molecules form dimer structures and a slip-stack column structure by stacking the dimers in the crystal as shown. It is this pi-stacked structure and pi-pi interactions that result in the magnetic properties observed. The molecules experience 4 different interactions in this arrangement at the 4 different points of contact seen. The stacked columns are connected by weak sulfur-sulfur interactions. This species exhibits strong antiferromagnetic interaction due to its dimer properties and weak ferromagnetic properties derived from its interdimer interactions. The second example is that of a trifluoromethyl Blatter radical derivative, which exhibits a reversible sharp spin transition. The first order transition proceeds via subtle changes of intra and interstack interactions between 2 energetically similar structural phases. The low temperature phase of 5 to 60 degrees Kelvin is diamagnetic, stemming from a multicenter 2-electron interaction. The high temperature phase at 60 to 300 degrees Kelvin, on the other hand, is paramagnetic as a result of non-interacting spins arising from weakly bound dimers. The change in arrangements takes place through slight changes in interplanar distance and degree of slippage along the stacking direction, which are critical to their magnetic properties. But what is the point of looking at these Blatter radicals and their magnetic properties? Well, actually, the potential of stable organic radicals to be used as multifunctional materials in electronic devices is becoming quite promising. The presence of unpaired electrons provides the opportunity to combine magnetic, optical, and transport properties in a single material. In addition to being able to change the side groups of the Blatter radicals and alter their physical properties, we can also tune these physical properties more finely using external stimuli such as heat, light, and pressure. Imagine knowing the kind of physical properties you want a material to have and being able to create it just like that. Well, by building up this database of knowledge around Blatter radical synthesis and property manipulation, scientists may be able to do just that. And that is all for today's episode of the Blatter radicals. If you were paying attention, you will now know about ferromagnets and antiferromagnets, about diamagnetic and paramagnetic species. You will know that it is possible to interchange between different magnetic behaviors by changing physical properties such as the temperature. And you will also realize that with Blatter radicals, nothing is straightforward or simple. Until next time with more exciting chemistry.